Hello, you guys. How are you? Welcome to Bio Cool, where studying biology is cool. And today's topic is radioactive dating. The subtopic is the carbon dating. In this video, we have dealt with carbon, atoms, proton, neutrons, quarks. How do we make carbon 14? How we use it in radioactive dating, and also some of the numericals to make your concepts stronger. And if you want such good videos every time from me, you can just subscribe to the channel and you can have all the updates for this. So pause the video, make your concept stronger. We'll meet you next time. Thank you very much.
Hi guys, welcome to my pool where you're studying biology in school and you know that. So in previous videos we were talking about the different kind of fossils like hard fossils, soft fossils, fossils where the fossil is the entire organism, fossil where fossil is a part of an organism. So all these concepts we have already talked in the previous video. We also talked about how the fossils are formed, like casts, molds, how entire organisms are preserved. All those concepts have been already talked to you, already been discussed with you in the previous videos. So what is this video about? This video is about a very important aspect in the fossils, that is dating the fossils. Now, it is a very basic concept that the question which I ask myself is why? Why am I studying fossils? What is the importance of fossils? The importance of fossils is that it helps us to study that what kind of organism used to live on the earth or biosphere XYZ years ago. Now the question is, how do we calculate that how old is the fossil? So if we are unable to calculate how old is the fossil, then what is the meaning of finding the fossil? In this video, I'll be discussing how do we calculate how old is a fossil. And for calculating how old is a fossil, we just use a term known as dating. So finding how old a fossil is, we call it dating a fossil. Now, dating a fossil, I'll be discussing in this video. There are actually 3 points I will be discussing, but in this video I will be discussing 1 point, and in another video 2 more points. So we are talking about today is the dating of fossils. Dating of fossils. Now, dating of fossils, we are talking here about radioactive dating. Radioactive dating, where we require some radioactive chemicals, as you know, elements to be much specific. And here we have one of the methods in the radioactive dating, we have one of the methods, the carbon dating. Another method is the potassium argon dating, which we'll be discussing in the next video. This video is all about the carbon dating. Well, the third topic, which is not the part of dating. So these two are the dating parts. The third one is not, of course, it's a dating, but not radioactive dating. It is something with electrons, something with nuclear magnetic resonance, NMR. It is known as electron spin resonance. So these are the 3 main methods we will be discussing in the dating of fossil. This one in this video, these 2 in the next subsequent video. Now, in this section of video, we are talking about the carbon dating. So let's move to the topic directly, that is carbon dating. Now, whenever I talk about carbon dating or any radioactive dating, one thing that should be clear in your mind is that we are talking about those elements which are radioactive. Now, to understand the radioactive dating or simply the carbon dating, we need to understand some of the basic chemistry. Now, students, this point is important. This I want to tell each and every student of mine that, or the subscriber, anybody who's watching, or anybody who's studying science or carbon dating or evolution, please, students, make it a habit of studying science as science. And what do I mean by that? For science, we would say like geography, science, science, right? I mean by that is, if you're a biologist, I've seen some biologists, they say that, okay, we are biologists, we need to focus only on the biological part of the topic. We study all the biological things. Let's skip the chemistry. Let's skip the physics. Let's skip the mathematics. But see, that is not according to me, a good learning. Good learning says that if you are studying a part in biology and if it involves chemistry or physics or mathematics, you should be knowing that physics, chemistry, and mathematics. Of course, I'm not telling you to get deep into that subject, all that calculus and all that complicated things and all that complicated physics, quantum physics, and all those things. I'm not talking about that thing. I'm just saying that basic thing, high school things, like high school chemistry, high school physics, or if high school mathematics is involved, you should be knowing that, and we should study a topic complete in all the aspects, not just biology, but chemistry, but physics and mathematics if it's involved. So I will be talking about this topic with emphasis also on chemistry and the physics and the mathematical tools which are applied in this carbon dating thing. And I'm not overlooking that, I'm not skipping that. I am going exactly to the chemistry, what it has involved. So if you know the chemistry, if you know the physics, you know the mathematics things, logarithms will be involved and some radioactive things will be involved. If you know the concepts, beta, decay, and all these concepts, you can skip to the further part of the video where I'm talking about more of the biology kind of things. But right now, let's go back to the chemistry. So when we talk about chemistry, let's talk about something about carbon. Now, and before that, let's talk something about radioactivity. What is radioactivity? Certain chemicals, they change into some other chemicals. For instance, let's say there is carbon 14. I'll tell you what is carbon 14. Carbon 14 converts into nitrogen 14, and while this conversion, it emits certain amount of radiations. Now, this radiation or energy which is emitted while conversion from carbon 14 to nitrogen 14, this energy released is known as radioactive. So this carbon 14 is said to be radioactive. Whereas, let's say there is carbon 12 or carbon 13, carbon 12 and carbon 13 forms do not decay into some other chemicals. So they do not release kind of radiation. So they are not radioactive. So why radioactive? So whenever we talk about the dating of fossils, we always focus on the radioactive isotopes of a particular element. For example, carbon. Now let's focus on the carbon. Now, what I know about the carbon is carbon is written as denoted by letter C. Everybody knows that. Very good. And it has an atomic number of 6 and a mass number of 12 in general. Now, here 6 represents, I'm going into very, very basic chemistry, guys. So if you know the part, you can skip to the further part. Okay. So C6 simply means that 6 is the atomic number of carbon. And atomic number is equal to number of protons in a chemical. Okay, proton, whereas proton is an elementary particle. Proton is an elementary particle made up of three other particles, made of three quarks known as up and a down and an up, down and an up. up is an elementary particle, down is an elementary particle. Sorry, quad. Down is a quad, up is a quad, up is a quad. And these three quarks are joined by some interacting forces. And these interacting forces are known as gluons. So gluons are the interacting forces, number one. Other thing is something known as up and something known as down. What is the difference between this up and down quad? The up quad, which is known as the up, let's have some mass. Let's not get into the mass. The important thing is the charge. It has a charge of positive 2/3. Now, why I'm discussing this kind of chemistry, this will help you know what exactly is happening with the carbon dating. So, pay attention. So up is plus 2/3, and down, my dear friends, is 1/3 in negative. So, up has a charge of positive 2/3, and down has a charge of minus or negative 1/3. Now, if we sum that up, there is 1 up and 2 up and 1 down. So 2 up together make up a charge of 2/3 plus 2/3, that is 4/3 in positive, and to that is added a down with a negative charge of negative charge of 1/3. So the total charge that comes on that proton has is 4/3 plus negative of 1/3, and that is the total of positive 3/3. Simple math. 2/3 positive, 4/3 minus 1/3, and that makes a positive of 3/3, and that is actually equal to +1. That's why we say a proton is +1 charge. That is a basic elementary school chemistry. The proton is made up of +1 charge. So atomic number signifies the number of protons. The number of protons, one proton means this. Okay, clear? Now, what about this number? This number 12. Now 12 represents the mass number. And what exactly is the mass number? Mass number signifies number of neutrons plus protons. So a 6 comes from here. 6 plus number of neutrons. Now, what is a neutron? Neutron is just like proton, again a particle which is made up of, again, 1 up, 1 down, and another down. So 1 up, 1 down, same like proton, but in spite of an up, there is a down. Now again, similarly like proton, it is also supported by interacting forces known as gluons. So that's for you, my dear friends, neutron. Now calculating the total charge on neutron gives us 1 up and 2 downs. Now 2 downs make up a charge of minus 1/3, that is minus 2/3. So these two combine and form minus 2/3. Whereas up has a charge of positive 2/3. So positive 2/3 is cancelled by minus 1/3 and minus 1/3. Hence, total charge on a neutron tends to be 0. So neutron is neutral, has a 0 charge. That's why known as a neutrons. So mass number is number of neutrons plus number of protons. So carbon 12 has 6 protons plus 6 neutrons. 6 protons plus 6 neutrons. I suppose I am clear on this. Now, let's get into some other things, and for that I am just erasing this up, down things. Okay, and I will also be erasing. Now what I am doing is I am adding, supposing this carbon has one more neutron, which is possible. Because if a carbon has one more neutron, it becomes carbon 13, where there are 6 protons and 7 neutrons. Okay? And of course, because there are 6 protons, the atomic number remains 6. Remember, atomic number is identity of an element. Supposingly, this atomic number is 6, it's carbon. If by chance I change it, I make it 7, then it is no longer a carbon. It now becomes nitrogen. And in nitrogen, who has an atomic number of 7, if I increase one more proton and make it 8, now it becomes oxygen. So remember that this thing is important. Carbon 13 is also carbon because atomic number is 6. Carbon for 12 is also carbon because atomic number is 6. Right? If I make it 7, it's nitrogen 12. If I make it 7, it's nitrogen 13. Getting my point? So atomic number is very, very important. It signifies the nature of the element. Signifies the name of the element. So it is carbon because it has 6. So you can change the 6. If you change the 6, you have to change the element. Okay. Now, carbon, any of the element does not exist in single form. It exists in many different forms. With same atomic number, because that same element is, hence the atomic number is same. So the same element can exist in different forms with different mass numbers. So is with the carbon. So carbon is present in abundance in carbon 12 form. That is approximately 98.9%. So majority of the carbon in nature is present in the form known as carbon 12. But there is also little amount of carbon 13 in nature, which signifies very little amount, that is 1.1% only. That is almost the remaining part of the carbon. And this is approximate values. So little, very little amount is also left. And that is taken up by the carbon 14. And this is of our importance because these two are stable and this one is radioactive. So carbon 14 is the one we are looking for. Carbon 14 is radioactive. It has like 6 number of protons, of course, because it's a carbon, and remaining, that is 8 number of neutrons. So that is for you, carbon 14, and it is radioactive, and it is present in very, very trace amounts, that is approximately 1 ppg, that is 1 part per thousand. Okay, so that is the value in atmosphere for carbon 14. Now, why is it significant? This is significant because with time, this carbon 14 with atomic number 6, what it does is, with time, one of the neutron, okay, converts into a proton. So one of the neutron from here, one of this guy, goes here and becomes a proton. So one neutron converts into proton. Okay, one neutron converts into proton. And that's possible because for conversion of a neutron into a proton, let's see what is the difference. We have an up, down, differences of this down and up. Up, down is common. What is the difference? Down and up. So if by chance, if a down gets converted, let's say this down gets converted into an up, this neutron will now become a proton. This neutron will now become a proton. So neutron becomes a proton, and it is not as simple as it seems. Why? Because we have to match the left and right. Right? We have a neutron. Okay, it converts into a proton. But if you see, here we have charge 0, here we have charge +1.
So here it's charge 0, here we have plus 1, and these are not balanced. So to balance it, we add one electron, minus 1. Electron has a charge of minus 1. So now this is 0 and this is 0. But whenever we add an electron, we need to add an entire particle. And there is something known as lepton number which has to be balanced. So there is something known as an anti-neutrino of electron, which is again released along with the electron. So this thing is released as energy, which is actually known as beta minus decay, minus beta decay. There is also a positive beta decay. There's also a positive beta decay. In that, a proton converts into a neutron, and what is released is a positron with a neutrino particle. I'll let you know. Let's write the reaction for the positive beta decay. Positive beta decay is just opposite of this. A proton converts into the neutron, and that is possible if this up converts into a down. And to balance this plus 1 charge here, we add a plus 1 charge here, and that is a positron, electron positron with a plus 1 charge. Okay, that is a positron plus 1 charge. And to balance again the lepton number, there is something known as electron neutrino is passed. Not anti-neutrino, but neutrino is passed. So that is the reaction, and that again is released as energy, and that is known as beta positive decay. But here we are not interested in the beta positive decay. Here we are interested in a beta negative decay, and that's what is happening when carbon 14, one neutron is converted into proton. So in the chemistry, what we need to focus is, let's get back to the focusing thing. This is the kind of radioactive physics. Let's I've told you this part. We can let's get back to the basic part, that one neutron is converting into proton. So now one neutron, when converts into the proton becomes 7, neutron becomes 7. So overall the mass number remains same. So mass number remains same. So the mass number is still 14. But the atomic number changes, and it changes to 7. And as soon as atomic number changes to 7, as I told you, the name of the element changes. Now it is no more carbon, it becomes nitrogen. So guys, this is for you, nitrogen. And now, I'm so sorry, I'll put it here. The mass number is same, the 14, but atomic number has changed 7. That's why it's now known as nitrogen, and it has become 7. So that is for you, the nitrogen. And now, what is of the significance? Significance is, this thing has a half-life, and is a half-life. This reaction has a half-life of 5730 years. 5730 years. Now, I will tell you something about the half-life. Now, before I talk something about the half-life, half-life simply means that how much time will a sample take, how much time will a sample take to convert to decay 50%. 50% decays occurs in what amount of time? So that is a half-life of certain decay. Okay, now I'll explain you that. Now pay attention. Supposingly, let's see on the board. Supposingly, we had, like, let's say we had 10 units of carbon 14. 10 units of carbon 14. Now, from this 10 units, I'm making two parts. In 5730 years, because that's the half-life, 5730 years, 5 units will get converted into nitrogen 14, because that's the half-life. Whatever it is, it's going to become half. If it was 20, it will have become 10. If it was 50, it would have become 35. If it was 100, it would have become 15. So starting at 10, 10 will convert into 5 of the nitrogen 14. Okay? And now, if what remains, what happens to the other 5? Other 5 is still carbon 14 with a half-life of 5730 years. Now, after another 5730 years, what happens is, this 5, what happens to become is, it becomes, let's say, 2.5. Half-life is 2.5. 2.5 becomes nitrogen 14. Okay? And, I'm so sorry, should I go here? Here. Okay. It becomes nitrogen 14 and the remaining 2.5 is still there as carbon 14. So the concept is every 5730 years it is becoming half. So how many 5730, how many half times are used? 1 and a 2. So after 2 half times from 10 units we have obtained 2.5 units are remaining. So 10 has decayed to 2.5. In how many half times? In 2 half times, half lives of the decay. Now, let's get back to the concept. Let's get back what is happening inside the biological concept. Now pay attention. Okay, let's get back how it is useful to us. How do we use it? Now, from this data, what we analyze is that from 10 units, let us name it amount at time 0. Amount at time 0. Okay. So these 10 units, from these 10 units, now remaining is 2.5. Remaining is 2.5. That is mean the amount n at time t. Okay. So n naught is the time, the amount of the carbon 14 at time 0, from where we need to calculate. Okay. And at time t, after some time, it has become 2.5. Now, the ratio of these two tells us how many times the carbon has decreased, and this gives us a value of 4. So 4 is the ratio of N0 by Nt. I suppose I'm clear. That means 4 times the original sample has decreased, and but it has become 1 by 4. You can say it has become 1 by 4. Now, what we see from this is that it decreases 2 times in 1 half time and decreases to 4 times in 2 half times. So 4 is actually, what is 4? 4 is actually 2 to the power 2. 2 to the power 2. So if we want to, so this gives us this value. 2 gives us number of half times. So if there was a question that tell me that there was a sample where we have 10 units of carbon, now there are only 2.5 units of carbon 14. So tell me how much time has passed. So we will calculate that it has decreased to 4 times. And 4 times means 2 to the power 2. So twice the half time has worked. Now after this, when we have got this number 2, what we'll do is we'll multiply it with 2 into 5730 years, and we will get to know that this time is approximately, let's say, 0, 6, 1, 4, 12, 10, 11. 11,460 years. So 10 units of carbon 14 decays into 2.5 units of carbon 14 in 11460 years. And how did we calculate that? We found out how many times did it decrease, and to reach that think what power should we raise to, and after getting that number, we multiply it by the half-life and we get an exact answer. So we can make a formula. We can make a simple formula. We can say 2 to the power x, 2 to the power x, where x is the number of half times required to reach to the certain amount, and that is equal to n0. That is the amount at time t0 and amount at time t, and that is the simplest formula you will ever see to find to do numericals based on the radioactivity. Now, this I have told you in radioactivity, carbon dating. What we are doing is we are taking a sample. We are finding how much carbon 14 is left. We by experiments know that how much carbon 14 was present earlier, or not normally how much carbon 14 is present, and now we relate the decay with the time, and analyze how much time would have passed since the decay has started. I'll tell you the biology. You will get a more clear concept of this. So remember this formula. We have got a formula where 2x is equal to n0 and nt, where x is the number of times the half-life has passed. Calculate the years. We will always multiply x with 5730 in the case of carbon dating, and n0 is the original amount, nt is the amount of carbon 14 at time t. Now I am telling you how do we use that same thing in biology. Now just understand this concept. We know that carbon 14 is very much less in comparison to carbon 12. We know that in biosphere, not in atmosphere, in biosphere, this is approximately 1.25 parts with the ratio of 10 to the power 12 parts. So 10 to the 12 parts of carbon 12 is in ratio with 1.25 of the parts of the carbon 14. So you can see that it is really less in number. But we know that in biosphere, this is the ratio, general ratio. Now, understand the concept. Let's say this carbon 14 is present in the atmosphere. What it does is, along with the other carbon, it combines with oxygen, and by certain steps, slowly and gradually, it's combined with oxygen, gives you a carbon dioxide. So now this carbon dioxide is not carbon dioxide with the carbon 12, it is the carbon dioxide with carbon 14. Okay, of course, carbon 12 carbon dioxide will also be formed, but now we are just focusing on the carbon 14 carbon dioxide. Now, along with the other carbon 12, this carbon 14 also gets along the formation of the carbon dioxide. And now, by basic biology, we know that this carbon dioxide is fixed by photosynthesis. Now, let's assume it that we have a plant here. Let's assume that there is a tree. Okay, now this tree takes in this carbon dioxide and converts this carbon dioxide into glucose. Now, animals use that glucose and break it down using oxygen and liberate carbon dioxide to the atmosphere. That's what is all about the carbon cycle. Very simplified carbon cycle. That atmospheric carbon is converted into glucose. That glucose in the form of starch is taken by the animals. Animals break down that starch into glucose again and use that glucose in glycolysis, oxidizing glucose into carbon dioxide, water, and energy, and the carbon dioxide gets back. So this thing is maintained now because this plant is in a cycle. Okay, this tree is in a cycle, and this animal is in a cycle of the fixing of the carbon dioxide. So amount of the ratio of the carbon 14 and carbon 12 remains maintained. Remains maintained because of this cycle. Now, as soon as the cycle breaks, and when will the cycle break? The cycle will break when either of them, this or this, either of them dies. So let's say this plant dies. So when this plant dies, now it is no more the part of the biosphere. Earlier it was part of the biosphere. Now it is a part of a biosphere. Means it is not become an abiotic component. So when it has become an abiotic component, it has died. Now it is not the part of the cycle of the carbon. Now what happens is, earlier it was in equilibrium. Now the equilibrium has break. Now the carbon 14 will decay. How will it decay? You know that it would decay at the rate, as I told you, it will become half in 5730 years. So what we do is, whenever we find a fossil, let's say we have found a fossil, what we do is we calculate the present amount of the carbon 14 in the sample, and for this we can use mass spectrometry. Mass spectrometry is a method which can be used to find out the carbon 14 amount. Now, after finding the carbon 14 amount, we already know that how much carbon is generally present in a living organism or a living plant or a living leaf. Now we know the amount of carbon which should have been present if it had not decayed. But now we know that it has decayed and there is certain amount. So now we calculate the ratio, that what it would have been before the death and now what amount is remaining. And that gives us a ratio. And we know how much time does it take to become half. We know how much time does it take to reach a certain ratio. So now we relate the decaying amount with the time and calculate approximately how old it might have starting, how many years back it might have starting decaying. And we know that it only decays when it dies. So we can say that how many years ago this fossil, this leaf or whatever we get was alive, how many years ago, just by looking at the present carbon 14 amount. And by carbon 14, because that's the one which is radioactive. So that's the whole dating thing, carbon dating thing is all about. Very simple, very much simple. Calculate the amount of carbon 14 remaining in a fossil, and we know from the data earlier that how much it should have been, how much it is now, how much has been the difference, and we know this difference is created in what span of time, and we just get the span of the time. Let's do some of the numericals on it to make it much clearer. Okay, so we will be doing 3 questions, 3 numericals on it, and numerical are appearing on your screen. And we're starting with the first one, and there is a very, very simple kind of a question. It says, a chemist determines that a sample of petrified wood, now petrification is a method I have already discussed in the previous video, and how it is a method of fossilization. Wood has a carbon 14 decay rate of 6 counts per minute per gram. Now, 6 counts per minute per gram is a unit of calculation of the amount of fossil remaining, and you need not worry about the unit because we are not here considering the unit. We are talking about the ratio. If someone says us that there were 500 grams and now it is 250 grams, so the ratio is half. If he says there were 500 kg and now it is 250 kg, so again the ratio is half. So if someone says there were 50 counts, now there are 25 counts, again the ratio is half. So the units do not matter right now in our calculations. Okay? So it only matters when we are writing answer. So if the unit is given to us in the counts per minute, then we have to give the answer in counts per minute. But we need not to worry about the unit because we are looking for the ratio, not for the units. Okay? So here the question is, it was again I'll read it. Chemist determines that a sample of petrified wood has a carbon 14 decay rate of 6 counts per minute per gram. What is the age of the piece of wood? That age is asked in years. The decay rate of carbon 14 in fresh wood today is 13.6 counts per minute per gram, and half-life is given 5730, which we already know. So see, we already know, we already calculate what is the amount of carbon 14 today in a live plant, and he is saying us that in a plant who has not died, see, we know he has already calculated the value 13.6 in the present plant. So that's what I was telling you. We already can calculate in a living plant. So in a living plant who has not died, you can say N0 has value of 13.6. Let's skip counts per minute for a while. We'll add it later in the answer. Now let's see. That's 13.6 is the N0 value. What is the value of NT? They've also given us the value of NT, that today it is only 6.0 counts per minute per gram. Okay, so 13.6 is the value in normal, that is, the same value would have been of this plant earlier, because sometimes, someday it was also a living plant, right? So this piece of wood, when it was living, it must be having the same value which wood present today has. Okay, that is 13.6. So at N0 can be 13.6, and today it has the value of 6.0. He's asking how many years must have passed. So to calculate this, he is asking us how many years, or we can say how many lives, or we can say how many years, as the language says. Now, to know it, we know the formula. The formula is very simple. I already told you this. It was N0 by NT, and we calculate a number by that, and that number is actually 2 to the power x, and x is this. How many years or how many half times? So we need to calculate the x. We need to calculate x, and that is very simple. Basic mathematics. What we'll do is we will substitute the values. We have 13.6 divided by, we have 13.6, and 13.6 is divided by 6.0, which is equal to the power x, and 13.6 divided by 6 actually comes around 2.2666667. So it is almost 2.266. So we take it almost 2.666. So 2.666 is equal to the power x. So what is this x? Pretty much simple. To calculate it, we take log. So we say log of 2.666 is equal to log of 2 to the power x. Now, in logarithms, we have a formula that anything which is the power comes into multiplication. See, logarithms are actually exponents. Supposing if we have 2 to the power 3, 2 to the power 3, and supposing if we have 2 to the power 3 to the power 2. So whenever an exponent has an exponent, we multiply. So 2 to the power 3 to the power 2 is actually 2 to the power 6. So it is multiplied. So similarly, when we have here x, that x in the power goes into multiplication. So here we have log 2.666 log 2 to the power x can be said as log 2.666 is equal to x log 2. Now to calculate x, we can take it under this, like this. We can write like log 2.666 divided by log 2 gives us the value of x. Now by calculation, if I use my calculator, the value of x comes approximately to be 1.1763. 1.1763. That is the value of the x. So that much times, that is the value, that much times at half time has passed. Okay, so it has decreased by, so I am telling you again, it has decreased by 2.666 times, and this 2.2 needs 2.66 times. It needs this amount of this value of half life, and we just need to multiply this now. Now x into 5730 that approximately gives us, like that is 1.1763 to 5730. That gives us the value of 6740 years. 6740 years. So that is the answer for us. That to reach. So six to reach a value of 6 counts per minute per gram from 13.6 counts per minute per gram, it needs 6740 years. So this fossil is approximately 6740 years. I'll repeat that again. How did we calculate it? We knew how much carbon 14 is normally present in a sample. We have calculated the amount of carbon 14 in our fossil. We took out the ratio, by how much did it decrease, how much time does it decrease, and to reach that amount of times, how many half-life must have passed. We raised to power to the x, and then we calculated the x. So x tells us how many half-lives have passed, and then we multiplied this x with 5730, and we got our answer. Now let's do another numerical. Now, let's do another numerical on the same type of question. And again, I'll be reading. There is a numerical on your screen. Again, I'll be reading it for you. The carbon 14 content of an Asian piece of wood was found to have 3/10 of that is living trees. How old is the wood? Now, it is just giving us the ratio. It is telling us, see, it's telling us now it has become 3/10. 3/10, that is 3/10. And it is giving a ratio that earlier it was 10. Okay, now it has become its third part, it's 3. Get it? So it is giving us an n0 value of 10, and now it has become 3. So 3/10 means if it was 10, it has become 3. If it was 100, it has become 30. If it was 1000, it has become 300. So that is it's telling it has become the third part. So indirectly it's telling us n0 is 10. That is the original sample, and now it has become third part of it, 3/10 of it. So 3/10 of the 10th is 3. So it has become 3. So we're giving us a ratio 3/10 in terms of nt by n0. But that is equal to 3/10. And you need a ratio reverse, that is inverse. That is n0 by nt. And that is 10/3. Okay? And again, applying the formula. What is the formula? Formula is 2 to the power of x is equal to n naught by nt. So that is our formula. So we know n0 by nt, and that is 10/3, and that is actually equal to 3.3. So 10/3 is equal to 3.3. So 2 to the power of x is 3.3. Now what we do is we calculate the value of the x. So therefore, calculating the value of the x, that what power should the x raised to get it 3.3, we take log. So we have log 2 to the power of x is equal to log 3.3. And we have again x log 2 mathematically. This comes into multiplication is equal to log 3.3. Now, simply using the calculator, it's directly equal to log 3.3 divided by log 2. And that is the value what we are getting for x. And that, if you use a calculator, it comes to be x is equal to 1.735. So that's the value of the x. Now, to calculate the years, we multiply this value. That is 1.735. 1.735 is multiplied by 5730 as we do it. Calculate the number of years. and those comes to be approximately 9944. So that is the amount of time in years that must have passed to make it 3 by 10. Now you can just relate it. If it would have passed, it has become half. It has become half of the earlier. So it would have been 5730 years. Now half is a lesser time. Okay, 3 by 10 is a more time. So in more time, it is always going to be higher than 5730. Okay, so our answer is 9944 years. If it have asked half, directly half, so here the ratio would not have been like 1.735. Here the value would have been 1. And when we multiplied 1 with 5730, it would have given us 5730. Getting my point? So let's get into so if it would have been becoming half, so here it would have been rather than 10 by 3, it would have been 10 by 5, and that would have been 2. So here would be having 2 to the power x is equal to 2, and now 2 to the power 1 is equal to 2 to the power x, and now x would have been equal to 1. Getting it? So this ratio is important. This x value is important. Okay. Now let's move to the next question. We are moving to another question for a practice, and that will be the last question. And after that question, I suppose you will be through carbon dating, how the numericals are solved for the carbon dating. The third numerical which we are facing is on your screen. That is, I will read it for you. Carbon 14 is used to determine age of ancient objects. Of course, we know that, nothing in that. If a sample today contains 0.060 milligram of carbon 14, it means that it is giving us what? Carbon, a sample today means it's giving us value of the amount of carbon today, that is NT today, time T is equal to 0.060 milligrams. Let's omit the milligrams. Okay, now what he's asking is, how much carbon 14 must be present in sample 11430 years ago? Now, he has twisted up the question. Rather than asking the time, he has given us time. So time is given. But time is actually given in a different type of way. But we need to calculate this N0. So our question is, how much amount would have been there this much years ago? Now, to calculate this, we need to understand for this amount of years, 11,430 years, how many half times would have passed. And we can calculate that. How will we calculate that? Very simple. We'll divide this 11,430, I suppose. Yeah, 430 will divide it by the half time of carbon 40, that is 5730 years. And this will give the number of half times passed. Means this will give us the value of that is equal to x. In our formula n naught upon nt is equal to 2 to the power x. This was our formula, and we will get x from this. And how many half times are passed? And when we calculate this approximately comes to be, if I calculate 11430 divided by 5730, it approximately comes to be 1.99. So this is the value of x. So we have got our x. We have our nt. We need to calculate n0. So putting everything in the formula, we have n naught upon 0.06. We can omit the 0 is equal to 2 to the power 1.99. So n0, value of n0 comes to be 0.06 into 2 to the power 1.99. So now calculating 2 to the power 1.99, it approximately comes to be, this value comes to be approximately 3.9972. In short, I'm taking. Okay, and I multiply this value. I multiply with this value with 0.06, and finally multiplying it with this value. After multiplying this value, after using this value, that is 0.06 into 2 to the power 199, I get a value of 0.238 milligram as being asked. So that is the amount of the carbon 14 that must have been there 11430 years ago. Okay, so this is the answer that we are got. I suppose by using this simple formula, we can calculate different numericals. We can practice different numericals. If you are stuck in some numericals, you can post that in the comment box, and I will make a video for that solution or give you a written solution. And in the subsequent videos, do watch if you have any doubts regarding the potassium and argon dating and electron spin resonance. So that's all about the carbon dating method. And remember, one last thing, I request everybody who's watching this video, who's studying biology, I'm telling you, never study biology or any subject in like just that subject. A biologist should always understand chemistry, physics, and mathematics as a tool, at least the high school level. Okay, that will give you a much clearer picture of the subject. So I suppose after this video, there are no doubts regarding the carbon dating. If there are any, you can ask me again in the comment section. And keep watching BioCool. We're studying biology in school. I'll take a leave from you. Thank you very much.